Welcome students. Last class we have started various sampling distributions. We have seen the sampling distribution of mean. In this class we will continue from the sampling distribution of mean, then we will talk about the sampling distribution of proportions and sampling distribution of the variance. Then I will introduce the concept of chi-square distribution. We will do some problems, then with that we can close this lecture. Before going to this lecture, just we will recollect what we have done in the previous class. Suppose this is a population. From the population I am taking as sample 1, say sample 2, sample 3, sample 4. For each sample I can find out the sample mean and sample variance. For example, if I write x1 bar, this is for sample 1 at its corresponding mean. If I say S1 square, it is the sample variance. So what will you do? This is for continuous variable. Continuous variable in the sense if I am measuring some length or height or something. Suppose if I take the same sample, assume that I am taking a discrete variable or the categorical variable. Categorical variable in the sense, see it can have only two values, positive, negative, or good or bad. Suppose I am taking, so this is sample 1, out of the sample 1 how many good products is there. So what is the proportion? So then I can call it as this is P1. We take another sample, that will be P2, another sample, that is P3. So if I plot this P1, P2, P3, directly I cannot plot it, first I have to construct a frequency distribution, then I will plot it, I will get another distribution, that is the sampling distribution of proportion. So there are 3 points here. One is first you take the sample, you take the sample mean. If I plot that sample mean, that will follow normal distribution. So mean of the sampling distribution is mu x bar equal to mu. The variance of sampling distribution is, I am writing x bar, that is sigma root n. This is my first result. What is the first result? From the population I have taken the sample. If I plot that sample various sample mean, that will follow normal distribution. Similarly, in this lecture what we are going to do, we are going to take some sample from the population. Each population is each sample is going, we are going to find out the proportion. So probability, proportion meaning probability. So I may get P1, P2, P3, that also will follow normal distribution. Okay. The third one which we are going to see in the class, so we have taken the mean. If you take the variance of each sample, if I plot that variance, which has come from normal distribution, that will follow a special shape. This is called chi-square distribution. Okay. This is going to be summary of our class, we will continue. Before that, from the previous class we have seen sampling distribution of the mean. With the help of sampling distribution of the mean, we can find out the lower limit, upper limit of your sample mean. That is done with the help of mu plus or minus z alpha by 2 sigma x bar. We will see how it is goal. Determine a range within which the sample means are likely to occur given a population mean and variance. So what they are asking, population mean is given, population variance is given, we have to find out the range of sample means, that is x bar, lower limit, upper limit. By the central limit theorem, we know that the distribution of x is approximately normal if n is large enough with a mean mu and standard deviation. Let z alpha by 2 be the z value that leaves area alpha by 2 in the upper tail of the normal distribution, that is in the interval minus z alpha by 2 plus z alpha by 2 encloses probability 1 minus alpha. So we can find out the upper limit. The upper limit is mu plus z alpha by 2 sigma x bar. The lower limit is mu minus c alpha by 2 x bar. Actually this has come from this formula, very famous x bar minus mu by sigma by root n. from this relationship we can set mu, if you readjust that you will get this equation. Okay. So, if you get from this you can find out the x bar. So, this value is x bar value, we can get the upper limit and lower limit of x bar is a sample mean. Okay. This was the what we have started in the last class. So, sampling distribution, there are three things which we are going to see. One is sampling distribution of sample mean, which I have seen. This class we are going to see the sampling distribution of sample proportion and sampling distribution of sample variance. First you will see sampling distribution of sample proportion. P equal to the proportion of populations having some characteristics, we can call it as P is the population proportion. The sample proportion we are going to call it as a small p hat. It provides an estimate of P. What is the meaning of this estimate of P is sampling distribution of sample proportion. We are going to use capital P is the proportion of population having some characteristics. Then sample proportion we are going to call it as P hat provides an estimate of capital P. So, what is the meaning of this one is, with the help of sample proportion we can find out the estimate of population proportion. So, here how the sampling proportion is found, equal to x divided by n. X is number of items in the sample having the characteristics of interest divided by n is sample size. The range of sample proportion is as usual 0 less than or equal to p hat less than or equal to 1. P has the binomial distribution, but can be approximated by normal distribution when NPQ is greater than 5. Here Q is nothing but 1 minus P. So, here it is following binomial distribution. As we know, the binomial distribution having a properties of having only two alternatives, that is good or defective, pass or fail, yes or no. So, only two alternatives there. Okay. So, what will you do? From the population we will take sampling proportion. So, when you plot that sampling proportion, that will follow normal distribution. Okay. So, what will happen? This picture shows different sample is taken from the population. For each sample we find out the sampling proportion. If you plot that sampling proportion, that will follow normal distribution. When we know that it is following normal distribution, it has two parameters. So, mean of that sampling proportion is, that is the expected value of your p hat is nothing but p, population proportion, and the variance of this sampling distribution is pq by n, that is a p into 1 minus p by n. Actually this need not remember this formula, we can derive it, because we know, we have seen in the previous class the mean of binomial distribution is NP, the variance of binomial distribution is NPQ. Actually we have to use capital P for the population. So, we will use capital Q, otherwise we can write 1 minus P. Suppose what happened, there is a population, I am taking proportion 1, proportion 2, proportion 3, proportion 4, like that I may get say P1 hat, P2 hat and so on, I will get many such proportion. If I plot this, sampling proportion, that will follow normal distribution. So, we have to find out what is the mean of this sampling proportion distribution. Similarly, what is the variance of this sampling proportion distribution. We know that since we have taken n sample from the population, so the mu p bar equal to mu x bar divided by n. Okay. We know that not mu, not x bar, mu x n. So, mu x we can write it as NP divided by n. So, that is nothing but your population P. So, what this result says, that the mean of the sampling proportion is equal to population proportion. Similarly, according to central limit theorem, this is sigma by, now when you square it is sigma square by n, sigma square by n. So, if you substitute sigma square is n p, I am writing 1 minus p divided by n, this is n square. So, variance is because when you sigma square by n. So, the z value for the proportion is, so small p cap minus capital B divided by sigma p. We know that sigma p is root of p into 1 minus p divided by n. So, p minus, so it is a small p minus capital P. Here capital P represents the population proportion, small p cap represents the sample proportion. We will do one small problem. If the true proportion of voters who support proposition A is p equal to 0.4, what is the probability that a sample of size 200 yields a sample proportion between 0.40 to 0.45. So, what is asked here is the population proportion is given, that is a 0.4, that is a 40%. What is the probability that the sample proportion will lie between 0.4 and 0.45? So, n is taken 200. If p equal to 0.4 and n equal to 200, what is the probability of p 0.4 less than or equal to small p, that is sampling proportion, less than or equal to 0.45. First we will find out the sigma proportion, that is the standard deviation of sampling proportion. Sigma p equal to root of p q by n. So, p is given 0.4, 1 minus 0.4 divided by 200, we got 0.034. We have to convert this one sigma p equal to standard normal distribution by using x minus mu by sigma p. So, x is given, x is your 0.4 minus, so we have find out the standard deviation of sampling proportion, that is a 0.03464. So, that will convert into standard normal, so that we can refer the table. So, p of 0.4 less than or equal to p cap less than or equal to 0.45 equal to p 0.4, this 0.4 is your x, the small p bar, minus the 0.4 is that capital P divided by 0.03, because that is your sigma p, that is nothing but this form, small p hat minus capital P divided by sigma p. So, p cap, that is the lower limit is 0.4, capital P which is given 0.4 divided by sigma p we got 0.03. So, this portion will get 0. The right hand side, see the another upper limit of p cap 1 is 0.45 minus 0.4 divided by 0.034, we got the p of 0 less than or equal to z less than or equal to 1.44. When you look at the table, p of 0 less than or equal to z less than or equal to 1.44, we can get 0.4251. So, we will summarize what we have done. It was asked what is the probability that the sampling proportion to lie between 0.4 and 0.45. So, what we have done, this 0.4 we have converted into corresponding z scale, it becomes 0. This 0.45 we convert into corresponding z scale, it is 1.44. Then we found this area between z value 0 to 1.44, which we got 0.4251. So, now we have seen this one, we will go to the sampling distribution of sample variance. Let x1, x2 and xn be the random sample from a population. The sample variance is sample variance sigma of x minus x bar whole square divided by n minus 1. The square root of the sample variance is called the sample standard deviation. The sample variance is different for different random samples from the same population, because every time you may get different sample variance. Okay. Very important result which you are going to see. The sampling distribution of sample variance has the mean population variance. So, what is the meaning in that one is, from the population you take different sample, for that sample you find the sample variance. So, mean of that sample variance is equal to population variance, but when you take the from the normal population if you take some sample, then you find the sample variance. If you plot that, that will follow a particular distribution. That shape of this will be like this, right skewed distribution. That distribution is called chi-square distribution, that you will see in the next slide. So, another important result is, if the population distribution is normal, then there is a relationship between sample variance and population variance. That is, that relation is n minus 1 s square divided by sigma square has a chi-square distribution with n minus 1 degrees of freedom. So, this x axis is nothing but n minus 1 s square divided by sigma square. This is nothing but our chi-square distribution. You may see there is a similarity between, there may be intuitively you can connect with the normal distribution. For example, we say that we will see in the next slide. For example, z equal to x minus mu divided by sigma. Okay. You take different x1, x2, x2 variables, so you will get sigma of x minus mu. So, what will happen when you square both side? When you square both side for different degrees of freedom. So, like that you take different sample, different means different x1, x2, x3. So, this will become sigma of x minus mu whole square divided by sigma square. So, the square of z, this is will become a chi-square. So, what is nothing but chi-square is nothing but sigma of x minus mu whole square. I think you know this formula, the variance is sigma of x minus x bar whole square divided by n minus 1 sample variance. So, this numerator can be replaced by, that is sigma of x minus x bar whole square can be replaced by n minus 1 into s square divided by sigma square, that is nothing but your chi-square distribution. So, there is a connection between your z distribution and chi-square distribution. The other thing, since it is squared, you see that z is normal distribution this way. So, chi-square distribution is like this, because you see that we have squared that z value, so that there will not be negative z. So, chi-square value will be always positive. That is the connection between your z distribution and chi-square distribution. What will happen? From the sample you have taken the variance, when you plot that sample variance, that will follow this shape. So, this x axis is nothing but your chi-square value. So, the chi-square distribution is a family of distribution depending on the degrees of freedom n minus 1. So, when the degrees of freedom is increasing, that means if you are started to take more samples from the population, then you plot that variance, at the end that will follow a normal distribution. What will happen? A chi-square distribution, when the degrees of freedom has increased, that will follow normal distribution. What is the chi-square distribution? From the population you take some sample, for that sample you find the variance, like that you take many sample, you will find a different variance. When you plot that variance, that will follow this shape. This shape is nothing but the chi-square distribution. What is this chi-square distribution? This x axis is n minus 1 s square by sigma square. Okay. Then another important concept, degrees of freedom, because many of the time we will use this concept degrees of freedom. We will see what is the degrees of freedom. Number of observations that are free to vary after sample mean has been calculated, that is the degrees of freedom. Suppose that the mean of 3 number is 8, say 8. So, x1 equal to 7, x2 equal to 8. What is the value of x3? What will happen? Since already the mean is known to us, we can supply any value to x1, any value to x2, but we cannot give any value to x3, because we have lost 1 degrees of freedom, because already we know what is the mean of that. So, what is the logic here is, when n equal to 3, so the degrees of freedom is n minus 1, 2. The two values can be any numbers, but the third is not free to vary from given mean. It is like example, like assume that there are 3 chairs there, we are asking 3 students to sit there. The first person who is entering will have 3 possibilities, that is the 3 degrees of freedom, because 3 chairs are available. The second person will have 2 possibility, that is 2 degrees of freedom. The third one, there is only 1 chair, there is no option for that. So, you have lost 1 degrees of freedom. If there are n values, you will have only n minus 1 degrees of freedom. Just how we have introduced what is the chi-square distribution and how it has connection with the normal distribution, we will do a small problem to understand the application of chi-square distribution. A commercial freezer must hold a selected temperature with a little variation. Specification call for a standard deviation of no more than 4 degrees, that is the variance 16 degrees square, it should not exceed 16 standard deviation 4. A sample of 14 freezers is to be tested. What is the upper limit of the sample variance such that the probability of exceeding this limit, given that the population standard deviation is 4, is less than 0.05. What is asking? What is the probability of sample variance that the probability of exceeding this limit is less than 0.05. You will see the next slide what is the exactly. So, first thing is we have to find out the chi-square value for n minus 1 degrees of freedom. This is the chi-square distribution. Here there are 14 samples there, the degrees of freedom is 13, 14 minus 1 13. So, the corresponding alpha equal to 0.05, 22.36. So, what is asked is if the chi-square value is 22.36, right, we know that the p of n minus 1 s square by sigma is 4, so sigma square is 16. If the chi-square value is 22.36, what is the value of your sample variance? That was the question. What is asked? The chi-square value is known to us, that is 22.36 when alpha equal to 0.05. When chi-square value is 22.36, what is the maximum value of your sample variance? So, probability of s square greater than k equal to p n minus 1 s square divided by 16 greater than chi square 13 equal to 0.05. So, this value right n minus 1 s square by 16. So, this s square nothing but your k. So, n minus 1 k by 16 equal to 22.36, when you simplify we are getting 27.52. The result is, if the sample variance from the sample size of 14 is greater than 27.752, there is a strong evidence to suggest that the population variance exceeds 16. That is the application of this chi-square distribution. We will see in detail, there are many applications for chi-square distribution. One of test of independence, another one is goodness of fit, that we will see in coming classes. Now we will summarize. In this class what we have seen, we have introduced what is the sampling distribution, described the sampling distribution of sample means for a normal population. Then we have explained what is the central limit theorem. Then we have seen the sampling distribution of mean. Then we have seen the sampling distribution of variance. Then we have seen the sampling distribution of proportions. Then I have introduced the concept of chi-square distribution, how it has connection with normal distribution. Then we have seen application of chi-square distribution. The next class we will go to the next topic, confidence interval. We will continue the next class. Thank you.